Okay, welcome everyone to this conference to celebrate IMPA's 70th birthday. It is my great pleasure and great honor to introduce the first speaker of this conference, Professor Ulrike Tillmann. Professor Ulrike Tillmann is a professor of mathematics at the University of Oxford and since last year, director of the Isaac Newton Institute. After finishing her early education in Germany, she got her PhD in Stanford. She has worked broadly in topology, K-theory, and non-commutative geometry, and has received multiple awards. Just to mention a couple of them, she received the Whitehead Prize from the London Mathematical Society in 2004, and more recently, in 2017, she has become a member of the German National Academy of Science. She has served in the scientific board of several international institutions. It's a great honor and pleasure to have her here with us to tell us about a renaissance for algebraic topology of manifolds. Please.
So first of all, I would like to give my warm congratulations to the Institute. This is really a true remarkable thing to celebrate the 70th anniversary, maybe for all of the Brazilian mathematical community indeed. The Institute, of course, has a worldwide fantastic reputation, so it's wonderful. Maybe, since you mentioned I'm the director of the Isaac Newton Institute, maybe I can give my official congratulations from the Institute. So I'm really honored to be the first speaker on this occasion, so thank you very much for inviting me. So an anniversary is a moment when to reflect maybe backwards. So 70 years is quite a long time. One might think, where did it start? Where are we now? And where the obstacles were, and what were the key moments to move forward. I want to do this here for a subject area, namely what I might call the algebraic topology of manifolds. This is a subject area, especially, I think, if you ask the mathematician on the street, they might say the algebraic topology had its heydays in the mid-century, 50s and so on. But for, in particular, recalling Tom Milner's work, Ware, Sullivan, Wall, Novikov, and many more, using computations, the computational power of algebraic topology to study, in particular, manifolds. Enormous advances were made. Cupboardism theory, we had surgery theory, we had in topological invariance of Pontryagin classes and many other things, and the field attracted many fields medals. But since then, despite some deep theory and beautiful ideas of Igusa and Waldhausen, somehow progress has been somewhat slow. And I think this has now changed in the last decade or so, and it's that change and why it happens and through what ideas that I would like to try to convey in the next 50 minutes or so. So, let me start, therefore, with the first thing. So what the algebraic topology of manifolds. Now, manifolds, I denote them by W. I tend to think of them as smooth manifolds and dimension D. Now, there are fundamental objects in mathematics, in geometry, topology, but also in applications. So when you have such a fundamental object, you ask, of course, yourself also, what are its automorphisms? So in particular, we ask here, what are the diffeomorphism groups? And if the manifold has a boundary, I will consider the boundary generally being fixed by the diffeomorphism. But instead of studying just one object, you often are interested in families of objects, bundles of manifolds. And then you're immediately led to ask yourself, what is the classifying space of that diffeomorphism group? I will get to that, make that more precise later on. And then, of course, from like in vector bundles, you might be interested in characteristic classes of your bundles. And so immediately you are asking about the cohomology. So for those of you who are not so familiar yet with manifolds, manifolds are those objects that locally look like a Euclidean space and maybe have a boundary, in which case it's half space. So let's just look at surfaces. Dimension 2 is actually quite an interesting case already. So we know of, of course, the classification of surfaces. The oriented surfaces are given by the genus G, and similar non-oriented surfaces can be classified similarly. And one way to write that WG here, I want to think of it as the oriented surface of genus G, but constructed as taking a torus and then forming the connected sum, G times. So this surface here, the genus 2 surface, is really a torus, well, tori, glued together, cutting out the disk, then gluing them together over the boundary. That is this connected sum operation. In dimension 2, the diffeomorphism of this genus G surface is very closely related, namely it has the same homotopy, as a mapping class group. Now, that is an object of fundamental importance also for geometric group theorists. A very interesting group, discrete group. It's just the connected components of this topological group. And so the classifying space of this particular group is very closely related to the moduli space of Riemann surface, another object that is studied from many points of view. Indeed, rationally, it has the same cohomology. The cohomology of this moduli space of Riemann surfaces, at least rationally, is the same as the cohomology of the discrete group, the mapping class group, and hence the same as the cohomology of our B-diff. And so the characteristic classes in this case are the same rationally as those for the moduli for algebraic curves. Okay, so I want to go straight into the a couple of main key results where I think actually things have changed in the last year. Okay, I have to admit that only a couple of weeks ago I gave the laudatio for Randall Williams and Galasius, who received the Clay Award, and in a way that is, I think, their key result. So let's start. What does it say? I do a similar construction like I did for the genus G. I take sort of the higher dimensional tori, Sn cross Sn, and take connected sum with itself, G times. So this is, in a way, a generalization of the genus G surface in a particular way. And then I want to have boundary, and so I take out a 2n disk. This is a manifold, of course, of dimension 2n, even dimensional. So what is the result? Well, here's a slightly easier stated result. If I just take any 2n-dimensional closed manifold W, and let's assume it is n-1 connected, that just means it doesn't have any homology up to dimension n, so to the middle dimension. And let's assume also that 2n is greater than 6, so we are talking about higher dimensional manifolds. Then, by gluing in this surface, on this higher genus analog, and I can take the limit, namely, when I have a diffeomorphism of one such thing, then I can extend over the genus G plus 1 by gluing in something. I have the identity, diffeomorphism identity on the boundary. I can just extend by the identity. And so I can form this limit. And the idea is that there is a map from this space into another space, which is a homology isomorphism. So that's good. If we want to understand this, that's very good if we do understand that. Now, this looks like a complicated space, an infinite loop space of something that I call MT associated to a spectrum. But the answer is yes, we can actually calculate that. Infinite loop spaces are part of stable homotopy theory, and in a way, stable homotopy theory is calculable, reasonably, in many cases at least. So, not to shortchange it, indeed, the theorem they prove is much more general. They have an analog theorem to this for any simply connected manifold and for all dimensions n, so even dimensions. And indeed, the theta that comes up here is some sort of, think of it as a tangential structure, and only depends on the n-1 skeleton going up to dimension, building your manifold, your space up to dimension n-1. Okay, so this is wonderful because it tells us something about the homology of this limit space, since we can compute this. However, people are generally interested in the finite piece. And you then immediately led to ask yourself, how does this limit space, or the homology of this limit space, relate to the finite pieces? And this is what is called homology stability. Namely, we can, the homology of one of these pieces is actually independent of G for G large enough. That's roughly twice the degree. So fixing the degree, we can compute the diffeomorphism of this particular manifold by just looking at what it is over here by the fit. So, for example, if we look at just this higher genus analog of the genus G surface, then we have a calculation. And the cohomology of this particular space, B diff, is actually just a polynomial ring over certain classes kappa C. And we know exactly what the kappa C's are, namely they are monomials, all the monomials in E and Pi in this dimension, where secretly these stand for the Euler class and Pontryagin classes in those dimensions. I will explain that a little bit more. But the upshot here is we can now compute a huge amount about these diffeomorphisms. And since I haven't really said that before, very little was known about any of these higher dimensional manifolds. Okay. So let's just look at what this does in dimension 2. Though I emphasized before here, this particular theorem was for greater than 6. The strengthening is actually true for all n, and in particular for n equal to 1. So for surfaces, we're actually recovering what was known as the Mumford conjecture or the Madsen-Weiss theorem. So here we now really look at the genus-oriented surface of genus G with a boundary circle. Madsen and Weiss proved in 2007 that indeed this limits space has a homology of a particular Thom spectrum. Again, we can compute it. And the homology stability was already known for a long time, namely by Theorem of Hare, proved in the mid-80s. So the upshot is, because of the, the close relationship between the different morphism, the mapping class group, and the modelized space of Riemann surfaces, the corollary is here that you prove that the stable homology of the modelized space of Riemann surfaces is just a polynomial ring in certain classes, the kappa I classes of dimension 2i. Okay, I'll now continue to try to give a little bit of a feeling what these characteristic classes are actually. So, construction. Now, we just for simplicity, let W be orientable, and we consider a smooth bundle over a topological space X. Then, of course, because every fiber is a manifold, we can sort of replace that manifold by its tangent space. And that gives me a vector bundle over the total space E. And tangent space, vector bundles have characteristic classes. In particular, I have a map that classifies this vector bundle. This is the associated, this is the Grassmannian manifold of D planes in Rn plus D. So if this is the associated classifying space, classifying map, then given a class in the cohomology of BSOD, so of this Grassmannian here, then we can define a particular characteristic class of our manifold bundle by first pulling back this class C, which is a characteristic class for the vector bundle, the vertical tangent bundle. And then, now this of course lives in the cohomology of E, but then we can do something what's called integration over the fiber. So we push down the class in cohomology on E down to the cohomology of X. And of course, it's called integration of fibers. If you think of it in terms of differential forms, literally you integrate D parts of it and you lower the degree. Sometimes this map is also called the Giesen map. Okay, so that's the construction. And indeed, this is the construction that we want to consider. Now, why does this lead us to characteristic classes in our modelized space? So a model for this B diff W we can get by looking at embeddings of our manifold W in very large Euclidean space. Take that dimension to infinity. And then, of course, on an embedding, I can let the diffeomorphism act by precomposing. So first do a diffeomorphism and then do the embedding. And that action is actually completely free. And this space here, sort of by Whitney embedding theorem, is weakly contractible. So really, we have here a model of this space B diff. And you can think of it as a topological modelized space. So a point here is just literally a manifold W embedded in R infinity, and that's your unparameterized, and that's your point in this. Now, if that is your point, then of course I have a universal W bundle, namely the bundle that over every point, which is a manifold, has all the points in that manifold. So that's the universal bundle, and we have that the isomorphism classes of W bundles are just given by the homotopy classes of X into this modelized space. Now that's completely standard and well known for characteristic classes. And so we have now the definition of a universal class C, for a universal class, characteristic class for W bundles. We can now take any C in BSOD and define it to be the characteristic class we just looked at on the previous slide and define that our universal one. Okay, so this is now living in the cohomology of BDiff. Now, in terms of the surfaces, this is exactly the construction that gives us the so-called Miller-Morita-Mumford classes, first studied by Mumford in the algebraic geometric context in the early 80s. And indeed, of course, BSO2 is the same as the cohomology of BSO2 is the same as the cohomology of CP infinity. So we just have a polynomial ring generated by one class, the Euler class, and the monomials in E are just its powers. So the only classes in this case are the powers of E to the I, and these are the so-called Miller-Morita-Mumford classes. Okay, so let me just go back. So here is the main theorem. This is what we might like to prove. And I want to just give a few ingredients of what this might, why do we see this, what ideas went into this proof and what made it interesting. Okay, so the first thing is I should really tell you a little bit about this space that I already said is very familiar from what we can study from a homotopy theoretic point of view. But it is made out of really familiar things, and those of you who have studied Tom's theory will immediately recognize what's happening here. Namely, it's just a slight version of the ideas there. So by definition, this space here is, well, a limiting space of taking maps from an D plus n spheres into this space here, which the C is here the one-point compactification of a space U perp dn, and U perp dn is just the orthogonal complement of the universal D-dimensional bundle that sits over the Grassmannian. So this is a Grassmannian of D-dimensional planes in R to the dn plus 1, R to the n plus d. So this is d-dimensional. I take the complement, that's n-dimensional, and I take the compactification. And then I take this limiting space of maps into it. Now, the notion here I just mentioned because of this shift, whether I take what sort of dimensional sphere I take map into here is just a matter of a certain shift of, just think of it as a degree shift in by spectrum. Okay, and this space here, the Tom class, is now in dimension minus d. And analogous construction can be done for other tangential structures. Okay. So that's one thing. So everything is relatively familiar, and then it's so familiar that I can just, on the one page, compute its rational homology. And I can quickly talk through it, but mainly to say this is nothing new, something that Tom would have done, and then it's in Milnor-Stashev, this calculation, really. Namely, I look at this limiting space. The first equality is by definition. The second one just says, well, I have Freudenthal suspension, so if I suspend, and then this becomes an identity for fixed degree. And then I can also take the maps here into the homotopy group, so I have just a degree shift, as I mentioned before. Now, this is a highly connected space because I'm taking the the one-point compactification of an n-dimensional bundle. So as n goes to infinity, this is it's very large, and this is very highly connected. So in those dimensions, there's a theorem by Serre that the rational homotopy is the same as the rational cohomology or homology. And now, of course, this space we have the Thom isomorphism theory, so it gives us just the homology of the Grassmannian. And so, applying Milnor-Moore, how homology turns into, how homotopy is related to cohomology, and I get the result there. So, again, this is coming back really to Thom's old construction. How do I find in my modeling, I have to define a map alpha from, so that's supposed to be a colon, not equal, from this space here to my infinite loop space associated to MT. And of course, a representative in this space, we said, well, it is just given by a manifold W sitting in Rd plus n. And I choose a neighborhood. So this is a schematic picture. The blue is my W, and the neighborhood is the black tube. And the lines show me show it to me as a vector bundle, namely as a normal bundle. And now, from this picture, I can define a map. Namely, if this is my Rd plus n, if I have a point in Rd plus n and it's outside the tube, I just send it to the point at infinity. Remember, this is a one-point compactification. But otherwise, I identify this with the normal bundle over W, compactified. And if I have a vector, V, that's the end of point of my little arrow there, then that point corresponds to this vector V, but also to a point X on my manifold. Okay? So in my normal bundle, I have a point X in W and V that's orthogonal to the tangent space, and I can just send that to the tangent space at W and V, which is a normal, an element in the normal. And that's exactly the map. How does this differ from what Thom did, actually? For those of you know, Thom actually did exactly the same map, only that instead of looking at the tangent bundle, he looked at the normal bundle here, the normal space. The advantages is that we can just stay, we can keep D fixed, and so we can stay in one dimension. And so what is the new sort of idea, or why did we even get to this stage? A new idea really, or new ideas came out of studying Cupboardism categories in relation to topological quantum field theory. Okay, what is a topological quantum field theory? Well, it's a map out of the Cupboardism category. It's a functor, theoretic monoidal functor from the Cupboardism category of dimension D into some vector space or something more fancy. And so, in particular, you are led to studying the Cupboardism category itself. And I certainly wanted to understand its classifying space. So what is the Cupboardism category? Well, the objects are in the specific model I'm taking here as D minus one dimensional manifolds sitting in a plane. So I have M0 and M1, both D minus one dimensional manifolds. And the Cupboardism is something that fits in between a D-dimensional manifold with M0 and M1 as its boundary. And how do you make this into a category? If you have two such pictures and they agree, say, on the M1, then of course you can just put them next to each other, glue them together, and you have a new D-dimensional manifold that's the glued together Cupboardism. And so you have composed your two maps. So we had a theorem that actually completely describes this classifying space of the Cupboardism category. What is a classifying space of a category? Well, you take a point for every object, you take a line for every morphism, you take a triangle for every composable two composable morphism, you take a tetrahedron for 3 composable morphisms, and so on. That's how you build it, and we proved that this is actually exactly the space that, of course, has come up before. However, I mean, it's a little bit roundabout way to describe this Cupboardism category. One way to see this space, what came out of this, right? When you compose here, you're just stacking things together, and you get really, what you're really studying, you can identify B Cup as the space of all D-dimensional manifolds that sit in this tube. So on every, over every point in R, you have something compact, and otherwise they can go on, grow on, grow and grow. Now that has to make sense of, and the topology has to be made sense of, and so on. But in particular, the topology tells you that if you have this long manifold, what you can do, you can always push things out. And what's important, why I'm saying this is, what is really important, you see, here you have all D-dimensional manifolds. And what Galasius and Randall-Williams had to look at is just what happens when you have the WG1s, you know, these higher dimensional analogs of genus G surfaces. You just have sort of one type of manifold. And in order to achieve that, you know, to go from all D-dimensional manifolds to just this particular type, they had to invent a parametrized surgery. So, for example, in order to get connected, right, they're all connected manifolds, what you do is you have 2 connected manifolds. Well, by this idea that I just mentioned, you can push them to infinity, glue them together there, and then bring them back. And that's sort of a viable homotopy, which then, well, obviously this is a schematic where you have to do it over all parameters and so on. That is what you want to do. Okay, so I have given you, hopefully, a little bit of an idea how that theorem goes. Why is this sort of a new way of thinking? Well, why should we expect new things here? So really, stabilizations, right? We sort of glued on more and more high-dimensional tori in order to get our result. Stabilization is actually something that has been looked at before. And generally, what you want to stabilize in the hope that the stable thing is an infinite loop space, okay? Because infinite loop space you can study with stable homotopy theory, algebraic topology should help. So before, what has been studied is to take your manifold, you cross it with an interval, and again and then again and again. So you make your manifold more and more flabby, if you like, and add more dimensions to it. And this limit space, in some sense, is computable via Waldhausen K-theory. And indeed, Igusa's theorem, a pseudo-isotopy theorem, tells us also something about the stability. So you can always infer some finite limit. So just to say a little bit more how this is supposed to go, you look at the concordances, so pseudo-isotopy, sorry. You take a C of M cross 1, which is really the diffeomorphisms of M cross 1, only that you have the identity on I cross the boundary of M and 1, you know, M cross 0. But on the top, M cross 1, you allow any diffeomorphism. So in particular, if you evaluate on the sort of on the top, you just get a diffeomorphism of M. And the fiber is exactly the diffeomorphism that fixes the whole boundary of M plus 1. But given this whole thing, the limit space of this, and taking classifying space, delooping, fits into an exact sequence, a fiber sequence, which sort of here we have the K theory, the algebraic K theory, associated to what you might think of the topological analog of a group ring, namely loops on manifolds and the sphere spectrum. So that's the definition of Waldhausen K theory. While, of course, in the approach we are looking at now, we are taking our W and we are connecting some, making it more flabby, but of course keeping the dimension the same. Now, the difference, I guess, is in some sense K theory we know is hard. It's very difficult to compute. And the Thom spectrum, which is the analog here, is of course relatively easy. I think I showed that. And then we have stability theorems. Igusa's stability theorem, you see, for a given degree, you never get beyond D. So D is fixed in your dimension. You never get beyond that. While here, of course, the dimension isn't fixed, but you can get some information as long as the genus increases. These are orthogonal approaches, but I think the second one at the moment yields loads of new results, and ultimately one probably wants to combine them. Okay, let me get to applications to really show we are sort of having a renaissance. Okay, so the first one, why? I mean, we seem to be looking at one particular manifold, namely this higher genus analog of surfaces. Why should it give us some other information? And this fiber sequence, I think, is one of the keys. So I want to look at the diffeomorphisms of my underlying, my manifold W. And then I just take a little bit from the boundary, so take a little bit from the boundary and a little bit neighborhood of that boundary. I keep that to the side, and I evaluate my diffeomorphisms on W, and I get an embedding. So here, this is one of these embeddings that I might get of W into itself, where I have to fix the boundary apart from a little neighborhood, apart from a little bit here. And so there's a sort of a, here, if this is an interval, there's a disk that spins around. And this space here, the fiber of this is, it's not too difficult to see, actually, that the fiber is homotopically just the same as the diffeomorphism of M cross a little interval, where M is a bit of the boundary that I do not need to be fixed. And then so this is the fiber sequence that Weiss considers, and Cooper's noticed that actually you can de-loop. So there's another factor here, so this is all still exact. And the idea being is that you need to find a multiplication on this in order to form this BDiff. And the idea here is that the multiplication that you get is that if you have a manifold cross an interval, well, then you can stack two of such things together, and you can use, in some sense, the interval glued to another interval is again an interval. You can use that in order to find a multiplication on this space here, and you get a de-looping. Now, why is this interesting? Well, you see here, this is where we can now maybe use our WGs and let G be as large as we want. This particular, the embeddings, there's something called the Goodwillie-Weiss embedding calculus, and that gives us some attack to this. So that means now that we can, in principle, also get information for any M here. And this is really has been very helpful. So for example, Cupid's, by just taking M, just an interval, or, well, sorry, an n-1 dimensional disk, he has been able to apply this and found that this classifying space for the different morphisms of D to the n is of finite type. So finite type is just a finiteness condition, so the homotopy groups in all higher dimensions are finitely generated. Doesn't sound so exciting. However, when you want to go on and do anything more, it's a really first step, and it's really important and surprising in a way that that hadn't been known before. And so by now using some more general M, and they were able to extend this theorem to be diff of M for finite type, has finite type for M closed, and these finiteness condition on M1. So there's a lot of history on this sort of condition, but this is a huge advance they have been able to make. Okay, so one thing that has been studied again, going back to Zieberman and Milner and so on, is the idea, well, how do smooth manifolds differ from just topological manifolds? So once you have a smooth manifold, you have diffeomorphism. Topological manifolds, you might just want to consider homeomorphism. How do these things differ? Does it matter whether I have a look at one or the other? And in particular, when you think about tangent spaces, smooth manifolds have tangent spaces that are identified by BOD, while topological tangent spaces are at best, you can just think of homeomorphism. So the homeomorphism and the, this is our orthogonal group. We have this map. And of course, well, not of course, it's known from the 70s, really, that if I take the limit over all the Ds, then the cohomology of these two things are just the same. And they're just given by polynomial ring on the Pontryagin classes, so each of these PIs has dimension 4. Okay, so we know, of course, it's very well known that in BSO2n, so that's the Grassmannian, cohomology of the Grassmannian, we have the relation that the Pontryagin class of dimension n in dimension n is the same as the Euler class squared. And for n plus k being bigger than n, then all these classes are 0, right? So the idea being I have an inclusion of this into BSON, and I can just pull back these Pontryagin classes, but they will vanish as long as for the higher case. Now, there's an obvious question, what about these classes which I can also pull back to top D, the homeomorphisms here? I can just pull them back the same way. Do they vanish? What's happening? And it wasn't ever formally conjectured, I suppose, but there was a lot of indication that they should just be 0, and the expectation was such. And indeed, Michael Weiss did spend a long time trying to prove that they are 0, until finally he realizes, and using the work of that I've been talking about, the theorem by Galasius and Williams, he was able to prove no, that's just not correct. There are many, they're all evaluate non-zero, so they're all non-zero. And just recently, preprint for a couple of months ago, Galasius and Mandel Williams actually proved not only are they non-zero, but actually this whole polynomial ring includes into B top D injectively. So all these relations are just not just not true, but they fail in the most drastic way. And as a corollary, so there's a map from the diffeomorphisms into the homeomorphisms, and from the homomorphism of the sphere, you can cone it off, so you get a homeomorphism of the disk, And so you have, from the disk, you go, and that is more or less by definition, the homeomorphism of R d to the d. And so it turns out that you can pull all these classes back, and you get an injection even into B diff of S2n. Now, these are, I think they're pretty much all new classes to be found. Right, so since we're already talking about diffeomorphisms of disks and spheres, this is, of course, one of the fundamental problems, right? What are the diffeomorphisms of S1? Well, S1 we do know. It's just S1 itself, basically. The rotation is everything you can do. So let me think of here all as orientation preserving. So I just get one circle. In S2, it's Smale, big theorem, and then actually diffeomorphism of S2 are homotopy equivalent. I don't mean equal, sorry. I should say homotopy equivalent. I'm afraid I'm a homotopy topologist, so they all come out as equal. Sorry, this is homotopy equivalent to just the orthogonal SO3. And in dimension 3, Hatcher proved that it's equivalent to SO4. And just recently, Watanabe showed this doesn't hold in dimension 4, the analog statement. And these, and here are immediate corollaries. So, in general, we do actually have that the diffeomorphism of the sphere are, well, certainly the orthogonal matrices give you a diffeomorphism of the sphere, and then there's always the diffeomorphism of a d-dimensional disk that fixes the boundary, right? Every can, of course, be extended to a sphere, diffeomorphism of sphere, by just gluing on the other disk and extending your diffeomorphism by the identity. So there's certainly a map from here into diffeomorphism of spheres, and actually there's a vibration sequence, and on spaces it's just a cross product. So this is true in general, in particular that tells us these things. But, yeah. And we also know that the connected components of these diffeomorphism of the d-dimensional disk that fix the boundary are in one-to-one correspondence to so-called exotic spheres. Now, going back in history, exotic spheres, Milner found the first one in dimension 7, got the Fields Medal for that, I think. And so here we are studying these exotic spheres, namely spheres, round spheres that have more than one differential structure. And indeed, we now have many new results on diffeomorphism of the d-dimensional disk, fixing the boundary, namely, let me show this one picture. Randall Williams with Coopers and with Kranich worked on these groups for even and odd dimension. This picture is, I think that's the even dimensional one. And what does it show? Well, we had Igusa stability, and that tells us something underneath this line. So this was known. Nothing of this was known above, and indeed, or very little, I should say. And all these red dots somehow are related to these Weiss Pontryagin classes, and where there's no shading, that's known, and there's some uncertainties in the other ones. So it's a huge amount. Okay, so let me just spend 3 minutes on my final slide. Another application, and this is an application to metrics on a Riemann manifold. So I take W to be compact, simply connected, and let's also make it spin. And G is a metric on W, so you can think of it as a section of certain bundle space. And of course, the space of all metrics is actually convex, so contractible. However, if you look at those metrics that give you a positive scalar curvature, then that's potentially a very interesting a subspace and has topology. And indeed, it was started by Hitchen in the 70s, who showed that the connected components are, first of all, it's non-empty, but it's also, we have potentially more than one component, and the fundamental group is non-zero. So there is interesting topology here to be had. So, but Winnick, Ebert, and van der Williams, using, again, these ideas of the stable homotopy and WGs, what they were able to show is that, well, this was a map that was already defined by Hitchen and Gromov-Lawson, namely an index difference from the space of positive scalar curvatures into a K-theory space. Okay? Now, they were able to show that sort of a certain reasonably known map related to the index, family index, into K-theory. This standard known actually factors through this space of positive scalar curvature metrics. And because we do understand this A hat, and it's actually a loop of that, that means, therefore, we can understand what this map does. And indeed, on homotopy groups, this map is surjective, and so this map is surjective. And so maybe the slogan to take away is that not only is this non-trivial topology, the topology is at least as complex as can be detected by index theory, or at least as complex as K-theory itself. And to go on, Ebert and Wiemehler showed actually that for W simply connected, so trivial fundamental group, these spaces are homotopy equivalent to just what happens on this round sphere. And Ebert and van der Williams previously had shown that actually for the round sphere, we have again an infinite loop space. Now, the hope is, of course, once you have an infinite loop space structure, you know you can use the methods of stable homotopy theory. So hopefully, we can now soon understand also the whole topology of this positive scalar metric space. Yeah. Okay. Thank you very much. Nice to stop here.
Are there any questions or comments for Ulrike?
Why the Theorem 1 rules out the case any dimension 4? The Theorem 1 you mentioned.
Sorry, do you mean the main theorem? Going back to the main theorem?
Rules out the case to n equal 4. Why
yes.
It's not considered the Wall stabilization theorem?
Dimension 4, as always, is a tricky one. And as I mentioned, surgery is playing an important role here. And you just need to have the sort of space you need in order to do the surgery. And the methods don't quite work for dimension 4. What is true in dimension, there's this limiting space that can be had, and that is actually true in dimension 4. What we don't have is this homology stability case. So it sort of understands the limit, but we don't know what's happening, how it's relating to a fixed finite four manifold. Which, of course, is somewhat, yeah.
I'll yell out and hope that you can hear me. Do you have any hold on how large G has to be in order that these things are true?
Yes, yes is the answer. I should have written it down because I don't have it in the top of my head, but it's very clearly, I think it's, I know in the surface case it's 2G over 3 roughly.
That's great. And the second question is not a fair one, but has there been any progress on the homotopy spheres?
That's not this, what this is supposed to do. Homotopy. There is there is progress, but the MIT and Harvard School has produced new results which are quite strong. But yeah, so there are some develops there as well. And maybe, I mean, I should say I'm very much presented this from one point of view, right? And I should also say, you know, though Randall Williams and Garces have done a lot in this field and maybe often the strong results, there's now a whole group of young people working there, and that should be acknowledged. There's also, and maybe that's what you're saying, the work of Mike Hopkins on the invariant, and that has seen a slightly different development, a more strictly homotopy theoretic development, calculating Adam spectral sequences, etc., which would answer your question.
Are there more questions? So if not, let's thank Ulrike again for her beautiful talk.